Have you ever just watched a piece of heavy machinery work and wondered, how does it move so perfectly? You know, how a robot arm can grab something with absolute precision, or how your car's windshield wipers clear the exact same path over and over again. Well, it's not magic. It's actually a super fascinating field of engineering. And today, we're going to pull back the curtain on the art and science behind it all, kinematic synthesis. All right, so here's the game plan. We'll kick things off with the core engineering challenge itself. Then, we'll get into the fundamental tools we use to solve it. From there, we'll walk step by step through a specific case study using modern software, see how we can level up that technique for even tougher problems, and finally, tie it all back to the real world. So before we dive into the how, let's really get a handle on the why. What are the kinds of real-world problems that push engineers to master these principles of kinematic synthesis in the first place? Just look at this backhoe. I mean, every single movement, digging, lifting, dumping, it's all controlled by this intricate dance of interconnected links. And believe me, this is no accident. It's a meticulously designed mechanism where every component's length, every pivot point, is calculated to achieve a very specific, powerful, and precise motion. And that right there is the central question for any mechanism designer. The answer is a process called kinematic synthesis. And what's cool is that it kind of flips the usual design process on its head. See, instead of building a machine and then seeing how it moves, we define the exact motion we want first, and then we design the machine that can create it. So how do we even begin to build something as complex as a backhoe arm? Well, we start with a building block that's surprisingly simple and really elegant. Let's break down this fundamental tool of the trade. At the heart of countless mechanisms is the humble 4-bar linkage. It's exactly what it sounds like, 4 rigid bars connected by 4 pivots. One link is fixed. We call that our ground. Then you have an input link where the motion starts and an output link where the work gets done. And that last link, the coupler, is the crucial piece connecting the two. Just by changing the lengths of these 4 links, you can create an absolutely incredible variety of movements. So here's the crucial point. We are given a desired output motion. Let's say we want this link to move from angle A to angle B. And we're given an input motion. Maybe this other link will rotate 30 degrees. Our job as engineers is to figure out the exact geometry of the machine that makes that happen. Now, the real challenge is figuring out the precise lengths of those links. And you could try to solve this with pages and pages of complex equations, but honestly, there's a much more intuitive and powerful way. Today, we use something called graphical constraint programming, or GCP. This is a method baked right into CAD software like SolidWorks, and it lets us solve these problems visually. It's a total game changer. All right, enough theory, let's put this into practice. We're going to walk through a case study and design what's known as a double rocker mechanism. That just means both the input and output links rock back and forth instead of spinning all the way around. Okay, here's our design brief. We have our givens, the fixed base is 4 inches long, and the output link is 2 inches long. We also know the exact start and end angles for both the input and the output links. Our mission, should we choose to accept it, is to find the missing pieces of the puzzle, the lengths of that input link and the coupler. Our method using GCP is a really straightforward 3-step process. First, we'll just sketch everything we already know. Second, we'll draw the linkage in its 2 key positions, start and end. And third, this is the fun part, we apply one final critical constraint and let the software solve the entire system for us. Okay, step 1. We start in our design software by just laying out the foundation. We draw a horizontal line and we place our 2 fixed pivot points, O2 and O4, right on it. This represents the ground link of our mechanism, the part that's bolted down and doesn't move. Now we start adding our knowns as constraints. We're basically telling the software what's non-negotiable. We say the distance between these pivots has to be exactly 4 inches. We define the length of the output link as 2 inches. And then we lock in all those start and end angles from the problem statement. Now, this is where it gets really interesting. What you're seeing here are 2 moments in time, basically frozen on the same screen. We draw the coupler link connecting the input and output for the start position, and then we draw it again for the end position. At this point, the software just sees them as 2 totally unrelated lines. And here it is, the magic moment. We select both of those coupler lines, and we apply a single geometric relation, equal. We are telling the software the most fundamental physical truth about our mechanism. The coupler is a single rigid bar.
Its length cannot change as the mechanism moves. It has to be the same in both positions. The second we apply that one constraint, boom, the entire sketch just snaps into place. It's fully defined. The software instantly calculates the two lengths we didn't know, the input link and the coupler. And just like that, we've gone from a simple list of desired motions to a fully designed, functional 4-bar linkage. Pretty cool, right? Now, designing a mechanism to move between 2 points is incredibly useful. But really, that's just scratching the surface. This same graphical method can be scaled up to solve much more complex problems. For instance, what if your part needs to pass through not 2, but 3 specific points in space? Well, that's called triple rocker synthesis, and the process is almost identical. You just sketch the linkage in all 3 positions, start, middle, and end. Then you apply that same equal constraint to all 3 versions of the coupler link. The core logic stays exactly the same. We can also use synthesis to control the timing and the speed of the motion. This is absolutely critical for machines that need a slow, powerful working stroke, but a really fast return stroke to improve efficiency. We call these quick return mechanisms, and you see them everywhere in automation and manufacturing. So let's zoom out and bring this all home. Why is understanding this process so important? Well, it's because these concepts are literally what allow us to build the mechanical world all around us.
I mean, every time you see a windshield wiper, a rock crusher, an engine piston, you are seeing the physical result of kinematic synthesis. Those simple lines and constraints on a computer screen become the robust, reliable mechanisms that do real work for us every single day.
Ultimately, that's the power of this process. It's the fundamental engineering bridge that lets a designer go from a simple idea, I need something to move exactly like this, to a physical working machine that brings that idea to life. So, the final takeaway here is that graphical constraint programming isn't just a calculator, it's a creative design tool. It empowers you to think about the motion first and then build the perfect mechanism to match your vision. So now that you have the tool, the only question left is, what motion will you design?